YAML, sklearn, linear model, lassopath. Description: the lassopath function in scikit-learn sklearn is used to compute the regularization path for the lasso model. It finds a sequence of models with decreasing values of the regularization parameter alpha and provides the corresponding coefficients for each model. Inputs: X. This is the training data. A 2D array with shape n samples. N features. Each row represents a sample, and each column represents a feature. Y. This is the target variable. A 1D array with shape n samples. It contains the values you want to predict. Outputs: Coefficients. This is a 2D array with shape n features. N alphas, where n alphas is the number of regularization parameters used. Each column represents the coefficients of the lasso model for a given alpha value. Alphas. This is a 1D array with shape n alphas, containing the regularization parameters used for computing the coefficients. Dual gap. This is a 1D array with shape n alphas, representing the duality gap for each alpha value. It measures the difference between the primal and dual solutions of the lasso optimization problem. Steps: The lassopath function iterates through a range of regularization parameters alphas. For each alpha value, it solves the lasso optimization problem, which minimizes the sum of squared errors SSE subject to a constraint on the L1 norm of pay. Coefficients: The function returns the coefficients, alphas, and dual gap for each alpha value. Metrics: Mean squared error MSE. This measures the average squared difference between the predicted values and the actual target values. Lower MSE indicates a better fit. R squared. This measures the proportion of variance in the target variable that is explained by the model. A higher R squared value indicates a better fit. Visualization plots: Coefficient path plot. This plot shows how the coefficients of the lasso model change as the regularization parameter alpha decreases. It helps visualize the feature selection process and identify important features. MSEVS alpha plot. This plot shows how the mean squared error MSE of the model changes as the regularization parameter alpha decreases. It can be used to identify the optimal alpha value that balances model complexity and performance. Fine-tune parameters. Alpha. This parameter controls the strength of the regularization penalty. A higher alpha value leads to stronger regularization and sparser models. Fit intercept. This parameter controls whether to include an intercept term in the model. Positive. This parameter controls whether to constrain the coefficients to be non-negative. Precompute. This parameter controls whether to precompute the gram matrix, which can speed up computation. Uncertainty methods. Cross-validation. This technique can be used to estimate the uncertainty of the model predictions. It involves splitting the data into multiple folds, training the model on a subset of the data, and testing it on the remaining folds. Bootstrap. This technique involves resampling the data multiple times with replacement and training a separate model on each resampled dataset. The variability of the model predictions across the different resampled datasets can be used to estimate the uncertainty. Challenges and fixes. Challenge 1. High dimensionality of data can lead to slow computation and difficulty in finding an optimal solution. Sample use case that resulted in challenge 1 when working with datasets with thousands of features. The lassopath function can become computationally expensive. Fixes to challenge 1. Feature selection before applying lassopath. Perform feature selection to reduce the number of features. Precompute gram matrix. Set the precompute parameter to true to precompute the gram matrix, which can speed up computation. Use a more efficient algorithm. Explore using more efficient algorithms like the coordinate descent algorithm. Challenge 2. Choosing the optimal regularization parameter alpha is crucial for model performance. Sample use case that resulted in challenge 2. When selecting a very small alpha, the model might overfit the training data and perform poorly on unseen data. On the other hand, a very large alpha might lead to underfitting. Fixes to challenge 2. Cross-validation. Use cross-validation to estimate the performance of the model for different alpha values and select the alpha value that minimizes the error on the validation set. Grid search. Use grid search to evaluate the model performance over a range of alpha values and select the best performing one. Challenge 3. The LaSopath function assumes that the target variable is continuous. Sample use case that resulted in challenge 3. When working with categorical target variables, the LaSopath function is not suitable. Fixes to challenge 3. One-hot encoding. Convert the categorical target variable into numerical variables using one-hot encoding. Use a different model. Consider using a different model like logistic regression for categorical target variables.